Okay, can anyone confirm that they can hear this? Can you just send me a quick message in either YouTube or Teams? I'll leave them both open here. Thanks, David. Yeah, okay. I got a new laptop. It turned out, ironically, my network interface card was the problem. So got a new laptop. The last one, I got 10 years out of the last one, which explains why the card went in the end. Okay, so I think this is running much better this time. I'm getting positive feedback from YouTube here saying everything is great. Okay, so you can send messages. I'm going to leave both Teams open. Now, Teams, there's going to be a lag. I know Teams is real time, but there's going to be a lag. But you can talk on Teams if you want, and I'll hear you here. I can't use Teams. I tested this last night. Teams just can't handle this at the moment for whatever reason. I know it worked last week, but I just couldn't get it working this week. So we're going to stick to YouTube. Okay, so I am actually going to begin this. I'm going to begin today just by this is where we left off the last day, and I'm going to begin today by moving on to the next the second of two routing algorithms that I want to talk about. So this one was Dijkstra's algorithm. You might remember from the last time. We were given a network like this. It's a graph, and you can see I've got what A, B, C, D, E, F nodes, 6 nodes, and I've got the link costs between them here. And the question was, use Dijkstra's algorithm to get the least cost path to all other nodes from E. So from E here, that was the question. The question could have been posed to go for D, A, B, F, or C. It could have been any of the nodes that I asked you to find the least cost path from. But to do it from E, I create this table over here, where each row of the table indicates a single iteration of Dijkstra's algorithm. So the 0 iteration here is really the initialization step, so it's not part of the loop. But in this case, for the initialization, I'm able to just write down information about those nodes to which I am directly connected. So here, E was directly connected to B, F, and D here as well. So I was able to put down it costs 10 to get to, it costs 10 to get to B, it costs 4 to get to D, and it costs 2 to get to F. So that's just the cost of those direct links, 2, 10, and 4. And beside that, I wrote comma E, comma E, comma E. The reason being E was the previous node on that journey. So that's kind of obvious in the initialization setup. It's the first node. Then once I had done that, I selected that link, which was the least cost of the 3 that I have here. Note the other 2 are infinity, by the way, but 2 is the shortest, because the lowest cost. So I circle that one, and I add node F to the list of nodes of which I know everything about. So F goes into that little box there. And once I've added F here, I then consider those nodes to which it is directly connected. Now I know my cost to get to F is 2. We've just circled that here in purple over here. I know my cost to get to F is 2, so I need to add on 2 to everything else that it's connected to. So in this case, F is only connected to one other node. It's B, so it's 4 plus the 2, which gives me 6. So I just check now, if I go to B over here, what's my current cost? My current cost was 10. Is 6 better than that? Of course it is. So I put down 6 here. I replace the 10 with a 6, and I put down comma F. Why F? Because F is the previous node to get there. So that's why I always have this comma beside it, so that you've got the cost to get there plus the previous node on the path to get there. Hence these two terms, the cost, the D to get to B, and the previous node to get to B. That's what those two terms mean. So unfortunately, F's not connected to anything else. So that was the only thing I can possibly change here. So everything else in the first row will stay the same. I've already added 2E, so I'm not going to put that down anymore. I know everything about F. Now I review the nodes I have here. I've got infinity for these two guys because I've got no connection yet. I noticed that 4 is the shortest cost. That was to get to D, so I add D to the list of things that I know everything about, and I review again. Now remember, the cost to get to D is 4, so if there's anything linked up to D, I have to add 4 to it. So let's see where we are. So we'll go to D here. D. I can get to C. I can get to A. So to get to C is going to cost me 1, plus that 4 is 5. So let's go to C here. What have we got? We've got infinity. Well, 5 definitely beats infinity, so I write down 5. Previous node was D. What about this one over here, A? That's 4 to get to there, plus the 4 again, so that's 8. What about A, infinity, infinity? So that's 8 is definitely better than infinity, so I write down 8, and the previous node was D. And everything else just comes down from the previous row. So now I review what I've got. 5D is the least cost path, so I add C to the list of nodes I know everything about. So here's C. So the cost to get there, of course, was 5 via D. So if I'm going to review the other nodes to which C is connected, I need to add 5 to that. So you can see C is connected to A and B. So 5 and 8 to get to B would be 13B. So I'll go to B. Well, I've got 6 already. I'm not going to beat that. So I leave that as alone. What about to get to A? I've got, what did I say to get to C was 5. So 5 plus 2 is 7. 7 to get to A. Is that better? Yes, that is better than what I have here. So I'll put down 7. I'll replace the 8D with 7 via C. I'll review again. This time 6 is the lowest. So I'll add node B to the list of things I know about, and there's only one node left here, which is 7C. So that's how you do it. So in the last iteration, I've just added A to the list of things I know about. Now the last part of the question here was, what was the least cost path to get from A to E? Well, if I want to figure that out, I just have to go to the final node here, E, which is, sorry, to get from A to E. So I go to the final node here, A. So the previous node on the journey from A was C. So I'll write down this. So previous node is C. So I go to C. Previous node was D. So I go to D. The previous node was E. So the answer is A, C, D, E. And that's Dijkstra's algorithm. So I don't think I need to cover that anymore. Can anybody just confirm? Can anybody at all just say that they're happy with that, or this video is working okay? You can use either Teams here, or you can use YouTube chat as well. Okay, so if you're happy with that, I'm going to move on to, I haven't got any feedback here. Oh, finally. Seems good. Thank you, Cian. Great stuff. Okay, so I'm going to move on now to, so that was our first algorithm. It's known as a link state algorithm. Dijkstra's algorithm is known as a link state algorithm. And now we're going to look at a new algorithm here, the second routing algorithm today. We're just going to quickly go over it, and I'm going to go through an example, which is the distance vector approach based on Bellman-Ford's equation. So it's different to the Dijkstra's algorithm in a few different ways, but they both use this same idea of a graph topology here for the network. So that's the starting point for both algorithms. So I'll leave this one up maybe. Actually, this would be way too complicated for Bellman-Ford, at least for me to calculate. It wouldn't be bad for an algorithm, but it'll be impossible for me to do it on the board here. So I'll do an example of a much smaller network with Bellman-Ford. But before I do that, because I haven't put the videos up, I'm going to go through the notes very quickly to get the basic ideas across. So bear with me. Okay, can you see that now? Can anybody see that? You should be able to see my slides, I hope. So anybody just confirm that for me. I'll tell you what, I'll keep going and I'll wait for that confirmation. I'll just be aware of it in the background. Okay, great. I've got confirmation there. Thank you, David. So I'm just going to go very quickly through the slides here. So you can look at the videos if you want a more detailed discussion of it. But yeah, I'll just very quickly go through the basics of it and then we'll maybe try an example of it as well. Right, so I've just covered the link state algorithm, and that if you just think about it, it's a global. It uses global information. So, in other words, the link state algorithm requires knowledge of all the link costs in the network. So, in other words, Dijkstra's algorithm needs to have a full picture of the whole network over which it's trying to calculate the least cost path, and that's very important because that's a very important point, because the next algorithm I'll show you, the distance vector approach, is a little bit different. It only needs to know about its immediate neighbors. That's all it needs to know about it. It only ever talks to its immediate neighbors in order to figure out the least cost path to other nodes that aren't its neighbors. So it's quite different to the distance vector. It's quite different rather to the link state algorithm. It's iterative, so that it shares that property with it's iterative, so it shares that property with link state, except in this case the iterations involve messages being sent to the neighbors in each iteration. It's asynchronous, so it doesn't have to happen in a timed way. In other words, these messages are going to come and go at different intervals. It doesn't matter exactly when they happen. They'll be sent at different times by different nodes, so they don't have to be synchronized. And it's a distributed algorithm. So in other words, each one of the nodes will be making some of the calculation independently of the other nodes and passing the information around. So it's distributed. So okay, so let's go through it. So it's based on this Bellman-Ford equation. The Bellman-Ford equation, it's fairly intuitive. So the idea is simply that if you want to find the least cost path from X to Y, so that's, I'll just highlight the slides here to show you what I'm talking. Just around here, I hope you can see my cursor. I'm not sure if you can. The least cost path from X to Y can be calculated as the minimum of, so we connect to each one of our neighbors, so we check the cost to each one of our direct neighbors V, and then we add on what will be the cost to get from that neighbor to our final destination Y. So it's a bit obvious, check neighbor 1. What's the cost to get to neighbor 1, and then what's the cost to get from neighbor 1 to where I want, and then do that for neighbor 2 and neighbor 3 and neighbor 4. So it's a bit obvious, really, but that's the basic idea of the entire algorithm, as you will see. And as always, the best way to teach these things is through an example. So let's look at this network, which is quite similar to the one I've just done on the board there a moment ago. So you can very quickly look at the graph and figure out what is the least cost path to get from, for example, V to Z. So V being up here to get to Z. It's pretty, you can quickly see it. You need to go 2, 1, 2, and that'll give you 5. A cost of 5. So if you go from V to X, X to Y, and Y to Z, you'll figure out it's 5. Similarly, dx to Z, so to go from X to Z would be just 3 here. 1 plus 2. So we go via Y. So that's fairly easy to calculate. Similarly, to get from W to Z, so our third node here, W, to get to Z is just 1, 2, right? W to Y to Z. So it's 3. So I can see the cost to get from V to Z, X to Z, and W to Z. I can calculate it fairly quickly in my head. Of course, that's not the way it's supposed to be done, but let's start off there. Now, if I'm going to run my Bellman-Ford equation to find the least cost path from U to Z, that's the node on the left, to get to the node on the right, I need to simply look at the minimum of 3 possible values because I've got 3 neighbors. So I look at my first neighbor V, the cost to get there is 2, and you see I've already figured out what the cost to get from V to the final place is 5. So it'll be 7. So CUV plus DVZ, that'll just give me 7 here, 2 plus 5. I do the same thing with X. To get to X is only going to cost me 1. And to get X to my final destination is 3, so 1 plus 3. And then finally, I do it for W, I get 5 plus 3. So the least cost path is therefore 4. So it's via X. And you can see it's just that path along the bottom of the graph. 1, 1, 2. Fairly straightforward. Okay, so another very important practical contribution of the Bellman-Ford equation is that it suggests the form of neighbor-to-neighbor communication that will take place here as part of this algorithm. So each node, so the basic idea is just shown here on the slide. Each node X begins with dxy, we'll say, as shown in the slide. That's an estimate of the cost of the least cost path from itself to node Y for all nodes in N, right? So, and then then follows an exchange of information with our neighbors. So we start off with dxy. That's an estimate of our cost to get to Y. It could be infinity at the start, and then X maintains that what's known as a distance vector. So it just keeps a record of it. With the distance vector algorithm, each node X maintains the following routing information. So we start off with this, the cost to our immediate neighbor. So we always remember what is the cost to our immediate neighbor. And secondly, what is the cost from our neighbor to any foreign node that we're not connected to. So let's see how this runs. I'll tell you what, I'm going to just jump ahead here to a practical example, and then I'm going to come back to this as a more formal definition. So we just jump straight into this example here. So at each one of the nodes here, and we start off with this little simple example over here. We've got these 3 nodes, X, Y, and Z. In fact, maybe the best thing to do here is to actually do this example on the board, on the whiteboard, and I can talk through it as I'm going through every single step. So give me a moment to wipe what's on the board. So while I'm doing this, I'll just put up the previous slide there. For you to read. Okay, back to the light board. Okay, so we'll start off with this little. It's a very small network, XYZ, and it has to be small in these examples because as you're about to see, the algorithm is it sends a lot of messages, and for me to the number of messages that are going to be sent is related to the number of nodes that are here. So I need to keep this fairly simple, otherwise I'll run out of board. So here's my network. The costs are 217. Okay, so we're going to run the Bellman-Ford equation now. I'm just going to write the Bellman-Ford equation up here for you to see again. So the Bellman-Ford equation what are the key points I've just tried to teach you so far? I know it's a bit squashed. Bellman-Ford equation, named after the guys that developed this. So I've got the least cost path to get from say x to y is equal to the minimum across the various neighboring nodes. So I check my the cost to get from x to each one of my neighbors plus the cost to get from that neighbor to the final destination. There's a hair here. That's what that is. It's not one of mine. You might have guessed. One of my kids. Okay, so dv to get to the final destination y here. That's the idea. So I need to look at each one of my neighbors v. Now, this is a really simple example. So if I want to consider each of these nodes, I only need to consider two neighbors. So that kind of keeps things a little bit straightforward here. Now, the other thing to remember here, the other important point in this question is, so the nodes, each node or router will maintain two things. Number one, they'll maintain the costs to get from x to v for all v. And number two, they'll maintain the estimates, current estimates we'll say, for getting from each neighbor to a final destination node in the network. So why, okay, this is such a simple example, every node is connected to every other node. But in a bigger example, y here might not be necessarily directly connected to us. There's only three nodes here, so it's a really straightforward one, but it helps to get the point across. So now each and every node here maintains its own equation here, so or its own table, its own routing table. So let's start off with x. Let's put our table down for x, and we'll have one here for y, and we'll have one down here for z as well. So the table will just look simply like this. I hope I'm not going too small here. If I am going a little bit small here, just let me know and I'll make it bigger. And it's x, y, z on the table. That's all the nodes in the network. X, Y, Z. Like that. Y, I might do this one in a different color just to distinguish it. So Y here would look similar, identical view. So they all have a view off the graph, if you like. X, Y, Z, X, Y, Z. And we'll put another color down here, make it a little bit different. Might be hard to see that. Hopefully you can see that okay. So right, so what are we calculating here? So this is from, this is the cost to get from here to here. So that's what the costs are. From here to here. From here to here. So let's start off with let's start off here, x to x. Well, that's obvious, right? That's 0, right? To get from, so this is the view that x has at the very start. So to get from x to x is 0, right? To get to y here is 2. And to get to z here is 7. Why do we know that? Well, we've just figured that out because we know the initial costs here, the CXVs here. So in other words, to get from x to y and x to z. What do we know about y? We don't know anything about y at the start. In other words, we don't know the cost to get from our neighbor y to our neighbor z. We just don't know that. We don't know what view y has of getting to x. Of course, these could be different as well. We could have different costs going in two different directions as well. That's important. That could be a nice question actually. Come to think of it, I haven't thought of that one before for an exam. But anyway, so if I could have costs different in the x to y direction to y to x direction, which we would start off with very different graphs here, which would be quite interesting. In any case, let's just go through this example. So y, to get from y to x, we don't know anything about it. So we just have to put down infinities here. We just don't know anything about these costs. To get from y to x, y to y, y to z, that's y's perception of things. We don't know what that is yet. That will require an exchange of messages with from one node to the next. So what about down here? X to get to x, we don't know anything about that. So if we're node y, we don't know the cost to get from x to the other 3 nodes. We just don't know. From y to x, we do know, right? Because we're y, so we know it's going to cost us 2. And to get to x, we know it's going to cost us 1 here. And we know to get to ourselves is 0. So 2 to get to x. And to get to z is 1. Now to get from, and we don't know anything about z's perception of things, so we just put down infinity costs here. Similarly down here, we just put down infinity for z. Z has no knowledge of nodes x or y. It knows about itself, so to get to x is 7. To get to y is 1. And to get to itself is 0. So that's how we start off. So we now exchange this information about our own. So we have new information here. The node has just filled in these values for itself, right? So is this one here. Oops, here and here. So the idea is now that this information about x's costs to get everywhere else in the network will now be sent to the other node, so they can learn this. So here we are again for x, y, z, x, y, z. So we already have this value here, 027 in here. And now we're going to receive this information here from y, telling us about y's costs in here. So we can write those two values in, 2, 0, 1. And from here we get information from z, which is 7, 1, 0. Now we have to recalculate things. So things are not done. This is just an intermediate situation. We've just learnt about the costs to our neighbors here. We've just learnt this new information. We've just learnt this new information here from our neighbors. So we have to recalculate our understanding of our own costs to get to all the other nodes based on this new information, based on the Bellman-Ford equation. So we know the costs to get to x. We know the costs to get to x to y is 2 and from x to z is 7. So based on this information and the cost to get from, for example, from y to z and z to y over here, we might end up with different end costs. So let's look at that. So we'll start off here for this one here. So we're going to revise this one. Let's check it. So the cost to get to y, that's c from x to so the cost to get from x to y is equal to, it's the minimum of 2, right? So it's the minimum of 2 possibilities. The cost to get from x to y directly plus the cost to get from y to y. That's 0, obviously. This one here. Or the cost to get from x to z plus the cost to get from z to y. So it's the minimum of these two things. So let's check these now. So this was 2 plus 0. That gives me 0. 2 on this side. 2 plus 0, comma. And over here to get to z was 7. And now we've just learned that to get from z to y is 1 plus 1 is 8. So clearly 2 is the winner here. Okay, so let's check the next. Let's check the next one here, z. So we're happy with this one. We'll leave that as it is. Wish it was easier to rub this out. So we'll leave 2 alone, and let's now check this 7 over here. See if this is still okay. So this means we check the Bellman-Ford equation again. So now we're getting from x to z. So we're going to go from x to z and z to z. And of course then from x to y and from y to z. So we're checking the two neighbours to see which one is going to get to the destination most cheaply. So what is the answer here? So to get to z is 7. That's our current value, plus 0. So that's currently 7. What about here? To get to y is going to cost me 2, and to get from y to z is only 1. So 2 plus 1, 2 plus 1. Obviously 3 is much better than 7. So I'll get rid of this 7 completely now. And I'll put in 3. So we're going to do exactly the same thing now for the next set of nodes down here for y. So I'll just get rid of the maybe it's better to just write the whole equation again for the Bellman-Ford equation again. Okay, so this is for the y node. So we got x, y, z again, x, y, z. Now, our previous knowledge of y was simply 2, 0, 1. Happy with that. This new information has come in from x via message in the second iteration here. So we've got 0, 2, so we've just learnt about x's least cost paths to everywhere else. And here from z as well. So fill this one up as well. So 7, 1, 0. I should just mention before I move on from x here, this has just been updated. Okay, so I'll just put a double box around that. So this is brand new information. We've recalculated new least cost paths. And when we have new least cost paths that we've just found, that means we have to go in the next iteration, we have to send these out to the other nodes. So we will have to send that out. That's where our next iteration will come. From X. Anyway, so we're down here. We've just learned this. We've just learned these guys. And these guys here. So let's recalculate our nodes using the distance vector equation once again. So we go back to Bellman Ford and we say, okay, well, what's the least cost path now to get to X? So I've got two possibilities. It's the minimum. So remember, this is the least cost path to get from Y to X this time. It's the minimum of getting from the cost from getting to Y to X plus the cost of getting from X to X, which is going to be 0 obviously, comma the cost to get from Y to Z plus the cost from getting from Z to X. And yeah, I mean, I know that that's going to, no matter what I do, it's going to be 2. It's not going to be any bigger than 2. I can just tell from looking at it. So you know, you can do the calculation there if you want. This would be 2 and this would be, I think, 8. 7 plus 1. So there's no need to do that. You can do the same here for the other two. You'll find that the distance vector equation just will give you back the exact same information. So there's no update here. So this is not being updated. So that means I don't have a need. So in this case up here, I had new updated information where I'm going to have to resend that now in a second. Here, because there's nothing, it's not new, there'll be no update, okay? No change according to the Bellman Ford equation for any of those 3 parameters. So no updates sent. And finally down here, we've got one more to do. You can kind of see now why I only do 3 nodes in this example, right? If I go for 4 nodes, I actually did 4 nodes one year, and I regretted it. Yeah, I really regretted that one. So that was a disaster. So X, Y, Z, X, and we already have 710. So we're about to receive this information here from X, which is 027, and we've received this information from Y, 201. So this is brand new information we just got. So now we revise our values here for 7. So we're going to, this time we're working with Z. So we're going from Z to X, which is going to be the cost to get from Z to X here, plus the cost to get from X to X. And then we're going to compare that with the cost to get from Z to Y, plus the cost to get from Y to X. So you can see this is going to be, to get to X, that's just 7 plus 0. And here it's going to be, to get to Y is just 1, plus the cost to get from Y is to X is just 2. So I get 3. So I'm going to end up updating this value here. It's gone to 3 now. What about 1? Well, I can tell it's not going to get any better than that, so I'm not going to bother with it. But you could do it if you wanted. But anyway, this is new information. So we've got overall new information here. So this is going to have to be resent to both neighbors. So that means this one is happy. It's not going to send any information because there was no changes here. This is a brand new update here. We've calculated based on these. We've calculated an improvement when we received these least cost paths from our neighbors. We figured an improvement out to get to our other neighbors. So so we have to update everybody with that new information. All right, one last iteration here. So everything stays the same at the moment. So 023, 201, but we've just received an update from down here, right? So we've got an update coming up here from Z with new information. Now it's 310. So we have to recalculate everything now to see if this is still okay. Well, obviously 0 is okay. What about y? Well, we have to run the Bamman-Ford equation on this. We'll find that it stays as 2. We'll do it for z here as well. We'll find that it stays as 3. So this is y here, and of course we stick with our 201 to begin with. We're just receiving new information from here. That's going to be 0, 2, 3, and we're receiving new information from down here as well, 3, 0, 1. And then we'll reevaluate our Bamman-Ford equation here, and we'll find that there's no changes. And then finally, same story with the third one. Same story with the node at z. We keep our 310 to begin with. We'll test it in a second. And we receive only information from here, from x. So we stick with 201, 310, and we receive new information from x, which is 0, 2, 3. And we find, if you do the maths, you'll find there's no new changes. So that's it. It stops. So let's go through what's just happened. Now, at all times, as well, we are maintaining. So at all times, each node also keeps a record of this. Okay, so it's not losing this information. It always knows. It always knows. For example, x always knows that the cost to get to y is 2 and to get to z is 7. So even though it has a least cost path here to get to z is 3, it still knows that its direct cost on its link is 7. It needs to maintain that information at all times. Any other thing to note here? Yeah, so note the messages that are sent. Every time there's a change, messages are sent from the node that's just updated to all the other nodes, updating it of its least cost information. So it does so in an asynchronous way. There's no need for these things to be timed. We don't have to send these routers can update intermittently and can just send updates whenever they need to, and that could trigger that could have a domino effect on the others. But it's completely asynchronous. They can do what they want when they want it. Each time a message arrives, it'll trigger a recalculation, but that might not result in any changes, and therefore it might end the sequence of messages being sent. Does anyone have any questions about that? Keen. Okay, Keen's happy enough. Right. So yeah, I mean it's pretty straightforward. It's not that bad. I will say I'm a little bit browned off with doing these in exams because they're so monotonous. These Bamman-Fords and link states. I'm finding them a bit tedious, and every year I look at the exam question and think, oh my god, I'm just putting in the same thing every year. So this year it is going to be a little bit different. I'm putting this in because you will find a link state or a distance vector in the autumn exams if you have to do them. But I've decided not to put in one of these this year, so there's going to be something a bit different. Now it's important you know this and you can be able to do this example, but I don't want to spend any more time on link state and distance vector. Okay, so I'm going to take a little break now and I'm going to move on to something I think is more interesting this year. Hint, hint. So we'll take a break, take a few minutes, and I'm going to go down and get a glass of water and I'm going to rub this out and I'm going to start fresh with some new topic. So we'll just set your clocks for 10 minutes maybe. I'm back. Oh no, I've got my screen over here coming in. Let's see if we can fix that. Yeah? What? Okay. I don't need that. Thank you.
But it's very important.
Okay. Where was I? So we're going to have a look now at we're going to look beyond those link state and distance vector algorithms. We're going to see, we're going to see how the network of networks, that is the internet, how cost information is communicated across different networks within the internet. So I think if I go through some slides, the point will become much clearer. And I need to say again, the much more detailed information will be going into the videos on all of this stuff. So, I am flying through some of this stuff at the moment. Okay, so we've just covered very quickly and through several examples what the link state and distance vector algorithms do. You've got this image, I hope, in your minds where you see a graph of different routers connected by different links with various costs, and we can calculate the least cost path very, very quickly using these algorithms. So that's what those algorithms do. It's for a smallish network. Let's move on now to something known as intra-AS routing in the internet, or OSPF. Hold on, I'll just check my I see some messages coming in there. Oh, it's not from this class. Okay, another class. Right, so where was I? Now I'm gonna fly through this stuff, and you can look at the videos in your own time for more information. So, so the study so far has been ideal. We've assumed all the routers are pretty much the same. We've assumed the network is flat. That's not really true in process. In reality, there's loads of different destinations. We can't just store all destinations in the routing tables. There'd just be too much information there. So even with those address ranges that I talked about, there'd still be too much information there. So Nuth has a couple of routers, or let's imagine Air or Vodafone or whatever, or different companies even with just several routers in their networks. They're all independent entities. These companies are independent companies. They do their own things. So the internet really is just a mesh of all of these independent companies with their own little, set of routers, all joined together. And that's what the internet really is. It's a network of networks. Each network administrator might decide to run things their own way. Some might decide to use link state. Some might decide to use, for example, distance vector to figure out least cost paths within their own network. So hence the intra as opposed to international, for example. So the idea here is that we aggregate routers into regions known as autonomous systems. So you can kind of think of a company maybe with tens of routers as being an autonomous system. So intra-AS routing is routing amongst the hosts and routers in the same autonomous system. In other words, in one network. And if we're all in one network, then all of the routers have to run the same protocol, be it your Dijkstra or your link state. So your company makes a choice, and then the company uses, say they choose link state Dijkstra, then the company says, okay, every router has to use this method, and that's how we're going to figure out least cost paths across our own network. And of course, a different company, a different autonomous system can do its own thing in a different way. So the gateway router at the edge of its own autonomous system has a link to routers in other autonomous systems. So there's always an edge router in any one of these autonomous systems that connects to another autonomous system. Otherwise it wouldn't be in the internet, right? So it has to connect to another network to be in the internet. Inter AS routing is different. So inter, as in like international, inter routing it relates to the routing that takes place as we move from one edge router to another edge router. So as we move from one autonomous system to another, how do we communicate best or least cost paths in that sense? We'll see how that's done using something called BGP in a few minutes. So interconnected AS router. So I'm really going to fly through this one here. So we'll imagine we've got AS1 here, AS2, and AS3. And there's two different types of routing algorithms being used here. We've got the intra routing algorithm, such as link state or distance vector, which figures out least cost paths within its own network. So that's the blue one. And then you've got the inter AS routing. So that figures out least cost paths to nodes outside of its network. And they both are used. Both of these routing algorithms are used to fill up the forwarding table. Okay, so let's go through some quick examples here. So suppose router in AS1 receives a datagram. So AS1 is down here. It's the bottom one here. Suppose router in AS1 receives a datagram from outside of AS1. The router should forward the packet to the gateway router, but which one? So in other words, imagine a router here has just received a packet that's destined for perhaps over here outside on the right hand side, or perhaps over here on the left hand side. How do we get it off the network? Or what? Like, we know we need to get it out of our network. We know it's not on our network. Should we send it to 1C to send it on its way over to the left, or should we send it to 1B to go to the right? So there's two gateway routers we can choose from here. So AS1 must first learn which destinations are reachable via AS2 and via AS3, and then it has to propagate that info to all the routers inside here, so that they all know which one they should send this datagram onto, and therefore whether they should send it to 1C or to 1B to get it off the network. And that's the job of inter AS routing, which we'll learn about now. But first, a few words on intra AS. So these are known as interior gateway protocols. Most common would be RIP, which is link state. OSPF is shortest path first. I think that's distance vector, if memory serves. And IGRP as well is another one that Cisco use, but they don't really tell everyone how it works. So OSPF is a link state algorithm. I'm not going to say any more than that. It's a link state algorithm, like you've just learned Dijkstra's algorithm. So it's called OSPF. It's just a version of Dijkstra's algorithm that's commonly used to figure out how to get around a particular AS. It has several advanced features. I'm just going to jump through it here. One of the most interesting things about OSPF is this idea of hierarchical OSPF. So we can actually break down our Dijkstra's algorithm into work in different areas. So for example, here we can have in this example here we've got area 1, area 2, area 3, and they're all connected to this backbone network. They're all independent areas. They're all connected to this backbone network here via some edge router or area border router here. And then the backbone has a series of routers as well, and at the top of it is a boundary router out of the AS, out of our network. But our network is broken up into several areas here. These routers in the backbone are known as backbone routers anyway. So we can now run for each of the independent areas, area 1, area 2, and area 3. We can run our own link state algorithm. It's independent link state algorithms. The idea being that if there's a datagram that needs to get that is not inside of our if there's a datagram destined for a node that is not inside of our area, we just send it to the area border router, and the backbone will figure out what to do. And of course, the backbone also runs its own link state algorithm as well. And it what's the word? Summarizes. If there's a datagram destined for area 2, that's just summarized as this one router here. So the backbone just sends it to that router. Okay, I'm just going to jump on here a bit. So I'm going to move on now to BGP, which is really interesting this year. So you might want to study this one. So BGP is our inter AS routing algorithm. So up until now, we've really just talked about our intra, so our link state or our distance vector. And now we're going to talk about how reachability is communicated across networks, from one network to a completely independent network. How do we communicate reachability information? In other words, how do we say, you can reach IP address X over here? How do we communicate that to other networks? And that is the job of BGP. So BGP stands for Border Gateway Protocol, and you can kind of think of it as the glue that patches all of these different independent networks together to create the network of networks, or in other words, the internet. And BGP has two key things. eBGP, which allows an AS to obtain reachability information from neighboring ASs. That's not ASs, as one smart ass pointed out in previous years, ASs. So eBGP it allows reachability information to go from one AS to another AS. iBGP allows new information that has just come in about reachability from another AS to be distributed within that AS. So let's see how that works. So again, examples are always key, particularly these types of tutorial style lectures. So let's go through this one here. So we've got our three AS networks here: AS1, AS2, AS3. Now the red dashed line here denotes the eBGP, or external BGP connectivity that goes on. That might be saying, say if AS1 is sending an eBGP message to AS2, it might say, look, you can reach this set of IP addresses over here. And then once that information has been received by 2A, for example, it then communicates that new information to all the nodes in its network, basically saying to everybody in AS2, if you have a datagram with this set of IP addresses, send it to 2A. Don't send it to 2C. I hope you get the meaning there. And then so that's done. The internal messages that are communicating this new information is done via iBGP. So these edge routers are really important in this discussion. So they're the ones that only the edge routers can actually run eBGP, and then all the routers can run iBGP. So BGP session. So let's go through some examples here. So we'll imagine we've got two BGP routers or peers here exchanging BGP messages over they do it over a semi-permanent TCP. It's pretty much permanent over a TCP connection. The advertising paths are sent to the different destination network prefixes. I'm going to show you some examples. And so we call this a path vector protocol. I've just got it in there in the slide. It's a path vector protocol because what's actually communicated is paths, as you'll see now in a moment. So let's imagine in this example X, and this is quite similar to something that might come up in the exam. Well, imagine X here is contacted here, or X is added to AS3 here. So how do we tell everybody in the world, if you like, in all the different networks, that X is over here? That if you have a datagram with the IP address for X, it needs to be sent on a particular path. How do we do that? Via different, in other words, it needs to hop over different networks. How do we communicate all of that information? Well, first, AS3 has just learned about X here as a member of its network, so it now sends out what's known as a BGP advertisement. This, of course, is part of the eBGP protocol. So it's sending a message, and it's known as a vector because it has information in there about the direction. So look, it says, look, if you want to get to X, you do it via AS3. So send it to AS3. That's the style of message. It's not exactly the format of it, but that's pretty much what's communicated. AS3, X. So AS3 promises, in other words, AS3 is promising to AS2 that if there's a datagram for X, that it will deliver it. So just send any datagrams for X to AS3 and it'll sort it out. That's what it's saying to AS2. Um, okay, so now we've got a preliminary understanding of BGP here. Let's get a little bit deeper. We're still going to brush over a little bit, but let's go a little bit deeper here. So there's two important path attributes that are being communicated in these vectors that are being sent. The AS path, that's the list of ASs through which prefix advertisements have passed, and then the next hop, which indicates the specific internal AS router to next hop the AS. Let's just jump into the example again to get this point across, because a lot of the time this is a little bit abstract until you see it working here. So let's start off here. Here we are again with X. X has just been added to AS3, so of course AS3 will start off by sending that message saying, look, if you want to send, if you've got an IP address for X, send it to me. So that's sent via eBGP from AS3 router 3A to AS2 router 2C. So that's very clear. I hope that's clear. So what happens next is iBGP. So now the internal BGP part of the BGP protocol now communicates. So its messages are sent from 2C with that information saying, look, if you have a datagram for X, it should be sent to AS3, but the next hop should be 2C. Does that make sense? So in other words, send it to me, send it to 2C, and I'll send it on to AS3. So based on AS2's policy, that AS2 router TC accepts the path and then propagates. Okay, so that's another important point here, policy. So there's a little bit more to the story here on policy. So this is where the whole idea of least cost paths is not necessarily the only answer when it comes to the path that will be taken. So this is the opportunity, if you like. BGP offers an opportunity to the networks themselves to make big decisions about how to route traffic. For example, network 2 here, AS2, might decide that it doesn't want anything to do with AS3. It might say, look, we're not going to send anything to AS3. They're a direct competitor. For some reason, we're going to just send everything to AS2 or AS1 and let it go that way. So these are the kinds of policy decisions that can be taken. Or maybe they've decided that a particular route isn't the way to go, that it should always be sent via a different route. Anyway, we'll meet that in a minute. So based on AS2 policy, usually the policy is just simply to accept it, but not necessarily. So let's say it's accepted here, AS3 X has just been sent in here, it's accepted, and now it's being sent to all other AS2 routers via iBGP. Based on AS2 policy now, the AS2 router 2A will advertise this new information to AS1. So you can see the vector here. It's now communicating that X is available through AS3 first through AS2. So we see that there's two hops, if you like, to get to X. And then that will be communicated within AS1. That will be communicated within AS1 via iBGP again policy dependent. So a gateway router might learn about multiple paths to the destination. So it's possible that, for example, here AS1 and AS3 are also connected via these two routers, 1C and 3A. So what happens then? So we'll say in this case, same story again, X has just joined, AS3 decides to send an eBGP message here, AS3X, gets sent to 2C. 2C then communicates via iBGP to everybody, including 2A. 2A receives it and then communicates via eBGP to 1C. And the message here is AS2, AS3. But this eBGP message would have also been sent to 1C from 3A. So in this case, 1C is now, after learning that X is available via two different paths. It's learned that it's available directly via AS3X here, using 1C to 3A, or it's available via AS2, AS3 from 1C to 2A as the first hop. So there's two different paths that could be chosen now by C. 1C can make a decision now. If it has a datagram for X, it has two paths available to it. So how does it decide which one? And again, that comes down to policy. So policy is really important here. And actually, there's a little bit of politics involved in this kind of stuff between ISPs as to how they handle, how they route traffic amongst different networks. So based on the policy here, AS1 router will choose between those two possible paths. And once it's made that decision, once it makes that policy decision, only then really does it, well, it will update via IBGP which is the route it's going to send it on. So it won't send both paths. It won't communicate both paths here to its own internal routers. It'll only communicate one path, the one that it selects via policy. So the BGP messages themselves there's various messages. I won't go into the details of the messages, what they look like. Let's have a look at the forwarding tables here. So how does the router set the forwarding table entry to a distant prefix? So let's go through this. So recall here that 1A, 1B, 1C learn about the destination X via IBGP from 1C. That should be hopefully clear to you now. So that's basically a message saying, look, path to X goes through 1C. That's all they really need to think about. It goes through 1C. Okay, so in that little graphic there, let's go back and do it again. So in this graphic here, you can see eBGP is used to communicate two different paths to get to X, and both of those paths are sent to 1C. 1C then, based on policy, decides to go at the shorter path, AS3, and then it communicates that via IBGP to 1A, 1B, and 1D. Thereafter, so what basically is that what 1A, 1B, and 1D are learning is, if I have a datagram for X, all I got to do is send it to 1C and it'll take care of it. And of course, if they were edge routers too, they would communicate the information via eBGP that AS3X is, or AS1 AS3X is reachable on that link. So now what happens? So let's imagine we have different costs here within our network here. Cost 1, cost 2, cost. So we've got two different. I don't know why I've drawn the 2 there twice, but anyway, we've got different costs within our in our paths here. So, say for example 1D. What's put into the table here for 1D is, look, X is reachable via interface. Oh, these are the links, the link names. X is reachable via interface 1 here, not via interface 2. So in other words, go in this direction if you've got X. That's the simple information that's entered into the table on X, or on 1D. And of course, that's the job. You know, that decision is based on. Sorry, I should have gone. So that decision is based on, you guessed it, your intra routing algorithm. In other words, your link state or your distance vector or whatever you want to call it, the OSPF and RIP and those ones. What about over here, 1A? Well, 1A will have this in its table here. Destination X is reachable via interface 2. So it doesn't have any further information. It just has, look, if you've got a datagram for X, send it on 2, then 1D will send it on 1 over here, and then it'll get to 1C. So that's the kind of low-level information that's actually maintained on the routing tables. They don't necessarily maintain path information. They just maintain next link information. What about route selection? So the router could learn about several different paths. In that example, we've shown 2 different paths, right? AS1 and then AS2, AS3. So there's 2 different paths. So how do we choose between them? Well, there's a few different options. You can go for a local preference. So you might prefer to go on one path based on some politics or policy. And you might go for shortest. You might simply say, look, let's be fair and go for the shortest possible route via the various networks. Or we could just, this is a really selfish one to do, next hop router. It's known as hop data routing. So in other words, if the datagram, if the router that's just received the datagram is closest to a particular edge router, then just pass it to that one. Who cares? Who cares about the least cost paths according to BGP? Who cares? Just get it off the network. Let's just wipe your hands off it as fast as possible. That's a very selfish thing to do, but it's one that's actually quite common, hop data routing. And it could be anything else. So I've got additional in here as well. So let's have a quick look at hop data routing here. So we'll imagine these are OSPF link weights. In other words, your link state Dijkstra's weights here, your costs, your least cost paths. We'll imagine this route has just come, this information has just come in that X is reachable. So AS3 here, the router 3A has just sent an eBGP message saying X is reachable via AS3. Then arrives here on 2C, and that information is communicated everywhere. And that simultaneously we get another eBGP message coming in here saying X is reachable via AS1, AS3. In other words, go to here, then pop over here. So both eBGP messages are perfectly valid. One is longer than the other, and anyway, both of them might reach 2D over here. So 2D via iBGP. So now 2D is aware of two different paths. So hop data routing. So choose the local gateway router that has the least intra cost. So in this case, if 2D has a datagram that's destined for X, where should it send it? Well, the right thing to do in my mind would be to send it over here to 2C and then get it over to 3A. But what it'll actually do is it'll just get it off the network as cheaply as possible via the other path. So the other path is available, so it notices that it only costs 201 to get it to 2A and off its network, and it'll cost 263 to go with the more honest path. So it ends up just going with 201 here and just pushing it over to 1C, which then gets to 3A. So it ends up sending it on a longer set of routers, but it does so, in doing so, it gets it off its network faster and more cheaply. Yeah, so there's other types of policy decisions here as well. So let's imagine we've got ABC here, our provider networks. They're all ISPs, we'll imagine, that are connected together, peers that are connected together. And we'll imagine that the smaller ones are customers. So we'll say A advertises the path AW to everybody else, to both B and C. And we'll say B might decide not to advertise, B might make the decision not to advertise BAW to C. And why does it do that? Because, well, why should it? I mean, B gets nothing from that route, right? So if you can imagine then Y wants to send something to W, why should B have to take that diagram? You know, Y would send it over here to C. Why should B have to be a hop on that journey? So it can decide not to bother advertising that at all. It makes nothing from doing that. So B gets no revenue for routing CBAW, since none of CAW are B's customers. So that's one of the decisions that's usually made. Also C will route, C will route CAW. So C here will route CAW, not using B to get to W as a result. So it's forced into that path. What about this point here? So X has two homes. So let's say you're Flash, you got loads of money and you decide you want two ISPs. Two is better than one, right? So maybe this could be a case for this if you have a company that is highly dependent on the availability of the internet. You may decide that it's best practice to be serviced by two ISPs, just in case one goes down. So let's say that's you over here, X, the customer, and you're dual homed. In other words, you have two ISPs. A policy you might have is to just not, because you are effectively a router connecting two different ISPs. You've become a router that connects two ISPs, and that will be communicated via eBGP if you allow it. So policy might be not to advertise paths. You might not advertise that you have a path to B via X in this direction, and similarly you might not advertise a path to C via X to B. So you might not want to do that, and for obvious reasons. Why should you? You're a customer, you're not an ISP. So policy is really interesting in all of this. So that's the end of what I wanted to say about eBGP, and of course you can tune into the videos if you want to get a more nuanced discussion about it. For now, I want to go back to the example and maybe step through it a little bit more. Sorry, I'm just trying to put up the whiteboard again. is the light? I think the light board is up. Let me just check YouTube. Yeah, great. Oh, there's questions coming in here before I go anywhere near it. No questions for me. Dara, unrelated to today's lecture, but for the exam, will it be a case that we have to upload solutions, or will it be a Moodle quiz, or is it decided yet? Okay, so Dara, it's going to be an exam paper, same format as always. So if you look through my exams, if you look through my previous exams, you'll see that there's that there kind of are open book exams. You know, it wouldn't really matter if you were sitting there for 2 hours with the book or not. You'd still have to figure out the answers based on understanding. So it's made no real impact to me in terms of how I designed the exam, except safe to say that I can't ask direct questions like, you know, what does BGP stand for or something like that, because that's a bit easy. But you know, I can still ask questions that just check your understanding, really, as I do. So you know, nearly all my questions are like that. They're nearly all checking your understanding of things. Next question here. So, can you have multiple backbone routers which also act as boundary routers? Yes, absolutely. So of course you can. So you can, you know, you've just seen in the examples we've gone through there that there was 2 edge routers on the ASs. So you know they could both be part of the same backbone. Yeah. Good question, Kian. Okay, I'm going to just draw the network there. I don't know if anyone else is asking. Actually, having two different chats open at the same time is a bit okay. No, I've checked everything. Okay, I'm up to date. Okay, let's go. Let's run through that example again very quickly. I just want to pose a few questions around the example you've just seen in the notes and see what you think. So right, so we had several different ASs. Sorry, I have to put it back up again because I've forgotten exactly what was on the slides. Okay, so here's what I had. I had a set of networks over here, or nodes. That was AS1, 1A, 1B. It doesn't matter. I had C here in the note slides. Wouldn't it be consistent, I suppose? 1C, 1D, and 1. Oh, I messed it. It doesn't matter. 1B here. Okay. And I've got another network over here. 2B here, 2A, 2D, 2C, and I've got a third one over here, which was 3, 3B, 3A, 3D, 3C, and we'll say X has just joined. X has just joined this network as well. And I think I had in this the last example I put up, I had something like different costs then as well. You know, for the link state algorithm that would run internally on the AS 263 152. That's what I had, and 112. We'll say that this is AS1, right? So AS1, AS3, sorry, AS2 down here. And of course these are going to be connected. So we'll just connect this node here, 1C to 2A. And we'll connect these 1C over here to 3A. I'm running out of marker. And 3A Let's connect to 2C. Okay. Now my question might be to you. Imagine now we've got, say, let's imagine this one is using OSPF inside. So let's say OSPF is used inside here to determine the least cost paths within the network. I would say RIP is being used over here, distance vector 1. I would say OSPF is over here. And of course eBGP and IBGP, nobody can choose that or not. That's the one we all have to use for intra and inter. So let's imagine now X has just joined here, and we'll imagine that yeah, so we'll imagine that 3C, this 3C or 3D down here has just learnt about X. So my questions would be, number one, how does so we'll assume initially so there's no connection here. So we'll just break this connection just at the start. Just imagine that connection is broken. Question one would be something like this. So how? So X just joined to 3D. Question one: how? Who is messaging me here? Okay, it's not you guys. So yeah. So how does 2B? Let's just pick any node here. So how does 1A learn about learn about X? Maybe I can phrase that a bit differently. Does 1A learn about X with eBGP, IBGP, RIP, or OSPF? Which do you think it is, based on what you've just learned today? So I can tell you what's going to happen here. So X has just joined here. So we're going to get an IBGP message coming this way. How is that the different color? Let's go blue. I don't know where blue's gone. We'll go to orange. So we've got our IBGP or eBGP coming down here saying X, comma, or AS3X. Then that's reached here by 2C. That sends messages to everybody in here. These are internal BGP messages. Sent in both ways. Sent, and of course this now sends information saying it's an eBGP message all the way over to 1C. IBGP, or sorry, eBGP. That then gets sent via IBGP everywhere inside here. So the answer is IBGP. Obviously, 1C here. Sorry, how does 1A? 1A is just learnt about it via IBGP. The answer, bingo. Question 2 might be the same question, say for same question. For 1C. Well, 1C, you can see it learnt about it via eBGP. So the answer was eBGP. And I could ask questions like that all day. Okay, so my next part of the question might be something like this. Once 2D has learned, so once question 2 over here, question 3, once 2D has learned about x, what path does it use to send x? Send datagram x destination datagram. So this is 2D down here. Which path could it be? Will it be on this path or this path? Well, you need to know a little bit more information. So you might be asked about, say for example, using the hot potato approach, or you might be asked to just simply go at least cost path. So if it's least cost path, you're going to go in. Sorry, if it's the least hop path, you're going to go in this direction. So answer would be least hop would go in the path. So if we have this connection in here now, we're going to end up with a reachability information coming down here via eBGP. I'll just use orange again. We're going to end up with information saying, you know, you can get to X via AS1, AS3 in this direction, and here you're going to get AS3X. So you're going to have two paths to choose from. So which one will 2D choose? It's going to choose, it depends on what you're going to do. If it's least hop, it's going to go with AS3X. And if it's hot potato, it's going to go with AS. It's going to just get it off the router here as fast, get it over here by a 201 as fast as possible. So it'll be AS1, AS3, X. Another question might be, you know, how would loops be detected? So we'll put down question 4 up here. Question 4: how might loops? Can anyone answer this one for me? How might loops be detected using BGP? Anybody want to answer that one for me? I'll wait for a second, give you a chance. It's kind of obvious when you think about it. Anybody? How many people are out there? Only 19 of you. What the hell are the rest of you doing? Anybody? Any of the 19 people that are there? No idea from Radic. Okay, so if there was a loop, right? So what do I mean by a loop? Imagine the diagram just kept going around in a circle. So a loop, because BGP is sending the path information every time. So for example, let's see. Imagine the diagram was to go. Let's imagine the diagram was. Let's say a path is just after being advertised via eBGP. Looked like, say, X is contactable by AS1, AS3, AS1, AS3. So this is a loop. It's just hopping. It's going around in a circle. So obviously it's detectable because it's a vector, right? So it's just it's taking note of every single hop. So if it ends up going back on its own path again, you can see it right there. AS1 is if the same AS appears in the vector twice, you've got a loop. I hope that's clear. I was hoping somebody would get that because that kind of means that you're not getting it overall. Maybe it was a bit too much information too quickly. Can I just ask for feedback there? Is it too much information too quickly? I mean, the videos aren't up yet for this, but I thought it would be better explained, maybe, or better introduced via these examples. Anyone want to give me some feedback? Radek seems happy enough with it now. Do I have time for one more question? I actually have a lecture after this. I don't know how I'm going to get the light board down. So that's everything I want to cover. Yeah, I don't really need to cover anymore, so it's nice timing, really. So okay, quick announcement. I'm going to put up a message on Moodle, just saying that if you have missed a lab, I'm getting lots of people emailing me asking about labs. The reason why I haven't let you look at the answers yet for most of the labs is because I've been getting so many messages here. I'm going to give you the opportunity to repeat the labs, for not if you've done the lab, only if you haven't done the lab because you missed it through for some reason, such as an interview, or you were sick, or your internet went down, or something like that. So if you've got a legitimate reason, you can do the labs again, the lab exams again on the last day of term. So I know that's not how you want to do your last day. Well, I suppose you can't really go to the pub anyway. But I'm going to give you the opportunity to do any missed lab exams. So what I'll do is I'll put up a timetable for the lab exams, and you can. And there's my next lecture. Wonderful. So I'll post that information on Moodle now, or tonight. And yeah, that's it. Okay, I'm going to sign off, guys. Have a nice evening, and yeah, thanks for sticking around, all 19 of you. Take care.